I hope to make math easy for you through this lesson. And in this lesson, we will be discussing about linear transformations, orthogonal matrices, linear dependence and linear independence and linear dependent vectors. We will also be learning about eigenvalues and eigenvectors. So consider the equations x dash equal to a1x plus b1y, y dash equal to a2x plus b2y. So we can write it in matrix form as x dash y dash equal to a1 b1 a2 b2 multiplied by xy. So this is a linear transformation in two variables. So we have converted xy to x dash y dash. Again, if we consider x dash equal to a1x plus b1y plus c1z, y dash equal to a2x plus b2y plus c2z, z dash equal to a3x plus b3y plus c3z. Again in matrix form we can write it as x dash y dash z dash a1 b1 c1 a2 b2 c2 a3 b3 c3 multiplied by xyz. So this is a linear transformation in three variables where xyz is transformed to x dash y dash z dash by linear transformations. Similarly, we can have a linear transformation in n variables where x1, x2, xn are transformed to n variables y1, y2, yn, and we write it as capital Y equal to ax. Y, ax are all matrices. If A is singular, the linear transformation is singular. You already know what is a singular matrix. We have done that before. Determinant A is 0. If A is non-singular, the linear transformation is called a regular transformation. So regular transformation, the matrix A is non-singular. The linear transformation y equal to ax is said to be orthogonal if it transforms x1 squared plus x2 squared up to xn squared to y1 squared plus y2 squared plus yn squared. The matrix of an orthogonal transformation is called an orthogonal matrix. And more definition, a square matrix A is said to be orthogonal if A into A transpose equal to A transpose into A is the identity transformation. So we'll do a problem based on this. Show that this transformation y1 equal to 2x1 plus x2 plus x3, y2 equal to x1 plus x2 plus 2x3, y3 equal to x1 minus 2x3 is regular. Write the inverse transformation. So we start writing it as, say, y equal to ax. So we have in matrix form y1, y2, y3 equal to 2 1 1 1 1 2 1 0 minus 2 times x1 x2 x3. So if we have to take determinant of A here, determinant of A is determinant 2 1 1 1 1 2 1 0 minus 2, and you can actually calculate the determinant. You will, when you expand, you get 2 into minus 2 minus 1 into minus 2 minus 2 plus 1 into 0 minus 1. So this is minus 1, which is not equal to 0. So since the determinant A is not equal to 0, A is non-singular, therefore the linear transformation is regular. So because A is non-singular, we can say that the linear transformation is regular. Now we have to find the inverse transformation. So the inverse transformation for y equal to ax would be x equal to A inverse y. And what is A inverse? A inverse is given by this formula 1 by determinant of A into adjoint of A. We have already seen how to calculate this in one of the earlier course lectures. So when you simplify, you get it as 2 minus 2 minus 1 minus 4 5 3 1 minus 1 minus 1. I am not showing the calculations because it was already discussed before. So coming to the fact that x equal to A inverse y, x will be A inverse, which is 2 minus 2 minus 1 minus 4 5 3 1 minus 1 1 multiplied by y, which is y1, y2, y3. And when you simplify, this is basically x, which is x1, x2, x3. So when you multiply the two matrices, you get x1 as 2y1 minus 2y2 minus y3, x2 as minus 4y1 plus 5y2 plus 3y3, and x3 as y1 minus y2 minus y3. So this is your inverse transformation. Coming to the next question, prove that this matrix is orthogonal. Now, when do you say that two matrices are orthogonal? If A into A transpose is the identity matrix. So A into A transpose would give you, this is A, and multiplied by the transpose of A. So this will be minus 2 by 3, 2 by 3, 1 by 3. The first column becomes the first row, second column becomes the second row, and the third column becomes the third row. So when you simplify, this would reduce to, you can actually calculate and see, you know how to multiply matrices, so you get 1 0 0 0 1 0 0 0 1, which is the identity matrix. Hence you can say that A is orthogonal. Coming to the next question, are these vectors linearly independent? Now, to check if vectors are linearly independent, what we do is we consider lambda 1 x1 plus lambda 2 x2 plus lambda 3 x3 equal to 0. First of all, when do you say that x1, x2, xn are linearly independent? So we say that x1, x2, x2, xn are linearly independent if I were to take a1 x1 plus a2 x2 plus an xn equal to 0, then if they are linearly independent, I have a1 equal to a2 equal to an equal to 0. So here I start with lambda 1 x1 plus lambda 2 x2 plus lambda 3 x3 is 0. So I have lambda 1 times 1 3 4 2 plus lambda 2 times 3 minus 5 2 2 plus lambda 3 times 2 minus 1 3 2. This will be 0 0 0 0. So equating the coefficients of x, y, z, w, you get lambda 1 plus 3 lambda 2 plus 2 lambda 3 equal to 0. Then I have 3 lambda 1 minus 5 lambda 2 minus lambda 3 equal to 0. 4 lambda 1 plus 2 lambda 2 plus 3 lambda 3 equal to 0. And 2 lambda 1 plus 2 lambda 2 plus 2 lambda 3 equal to 0. So I have to solve these four equations simultaneously and get the value of lambda 1, lambda 2 and lambda 3. Now, if I were to call this, say, 1, 2, 3 and 4, if I were to do equation 4 minus equation 1, in that case I would get lambda 1 minus lambda 2 equal to 0, which implies lambda 1 equal to lambda 2. Now you are free to choose your own operations. It doesn't mean that you have to use the same thing. Anything which makes sense and mathematically right is fine. Now if I substitute in equation 3, so from equation 3, if I put lambda 1 equal to lambda 2, I get 4 lambda 1 plus 2 lambda 1 plus 3 lambda 3 equal to 0. That would mean 4 lambda 1, I get 6 lambda 1 equal to minus 3 lambda 3. So I have lambda 1 equal to minus half lambda 3. So what do we have here? Lambda 1 equal to lambda 2 and lambda 1 is minus half lambda 3. So if we can say that the vectors are not linearly independent because you are writing one as a linear combination of the other, and because you are writing them as a linear combination of the other, lambda 1, lambda 2, lambda 3 cannot be 0. So the vectors are not linearly independent. Now if A is any square matrix of order n, determinant of A minus lambda I will be determinant A11 minus lambda A12 A1n. Second row would be A22 A22 minus lambda A2n. Nth row would be an1 an2 ann minus lambda. Now if I were to